to know what the equations are. For every test where we have equations, I'll give you an equation sheet that has all the equations on it, but you have to know which one to use and how to use it. So you don't have to waste time knowing, oh, wait, was that 1/2 rho u squared? What you do when you say, oh, it's a Bernoulli equation problem. There's Bernoulli's equation. Here's what I plug in and how. Okay? Is that clear? People are looking confused. You have to know the equations. You don't have to memorize them. Anyway, here's Bernoulli's equation. And it basically just adds up the total energy in, say, 1 cubic meter of fluid. And how many of you guys have dealt with this before at some point? A couple of you. You can see that we can change these different properties. So if I've got this much energy in a fluid, like air, let me get it. It'll be a good one. This much energy in say, air, and I change the energy by, say, blowing across the top of a piece of paper, I'll be raising the kinetic energy, right? And it turns out that you raise this, you lower pressure to compensate. And so this is why the Bernoulli's equations explains why airplanes fly. If you blow across the top of a piece of paper, it lifts. And that's why airplane wings are shaped like this. It's a longer path. Here's a simple way of explaining it. You've got air, nice cubic meter of air sitting there happily enjoying its sunshine day up in the atmosphere. Or it can be a packet of water in the ocean, and suddenly a airplane comes by and slices through it, and the water underneath, round that off, make it more aerodynamic, the water underneath the wing goes by the wing like that, has the wing go through it like that. The water on top of the wing has a longer path to travel, so it has a larger velocity, so pressure decreases. And therefore, you provide lift. Everybody understand that? Okay, so now, I use the wing thing, but to sort of give you the perspective, now imagine, this is why we do it in this class, imagine you're on the bottom of a river, and you're a happy little pebble sitting on the bottom of a stream, and the water touching your pebble isn't moving at all. That molecule of water isn't moving at all. Just above it, we have a stream flowing along. What's the pressure difference from there to there? Is it you're going to get the same effect? Mm-hmm. Yeah. And so there is a lift that's provided by the Bernoulli equation that is proportional to the square of the velocity. So in other words, the faster the river flows, or the wave, or any current, any fluid, wind blowing over a sand dune, the faster it flows, the more it tugs at sediment lying on the bottom and tries to pop them up into the fluid so that they'll move. Make sense to everybody? This is the main reason why wind and water carry sediments. there are what we call viscous drag effects, which is basically you've got the water and it actually will push on a rock or pebble and kind of push it down the stream. But by far, and with really big rocks in the middle of a river, this is a big effect. But for most sediment, it's the Bernoulli effect that's the most important thing that what we call entrains sediments, pulls them into the flow and starts them moving downstream. Okay, questions? So let's do a couple of trial problems. Break out your calculators. All right, so calculate the total energy of water in a lake that's 100 meters deep. I'll work through this one with you. And so first let's do the Bernoulli equation. The energy, the total energy in the fluid is equal to the density times the depth of the fluid times gravity plus 1/2 times the velocity squared times the density of the fluid, kinetic energy, plus the pressure. So if we're looking at 1 cubic meter of water in a lake, what is the total energy in that water? First, what's this number here?
Density of water.
Yeah, which is?
1.
1,000. 1,000 kilograms per cubic meter. What's this? What's this? And what's this? Huh? Somebody? 0. Yeah, this is 0 because we're in a lake. And what about this?
0. That's equal to.
Yeah, if we're at the top of the lake, it's 0. If we're at the bottom of the lake, that's 0, and that's the same. So these two add up to this at the top of the lake. So give me a number. Everybody do it. If you don't have your calculator, try using just do it longhand. Did you go? Right. Would be 980,000.
Mm-hmm.
Everybody got that? Anybody not get that? Okay, so now tell me